Now we are ready to learn this new type of integral called a line integral. So we're going to start with a function. So we'll start with a two-variable function, f of x, y, and we'll let it be continuous on some region containing a smooth curve C, where C is going to be given by some parametrized curve. So say r of t is x of ti plus y of tj over a to b. Then what we're trying to compute here is we're going to integrate over that curve C. We'll integrate the function f of x, y, and we're going to do this ds, where that stands for with respect to the arc length. Often S represents arc length. And so this line integral, the way that we're going to actually compute it is we're going to convert it back into an ordinary integral, where we're going to go from a to b, and we're going to convert this into an integral with respect to t, which is the parametrized variable of our curve. So we're first going to, in the function f, we'll replace x with that x of t component. We'll replace y with the y of t component. And then we're going to multiply this by the square root of x prime of t, quantity squared, plus y prime of t, quantity squared. And this whole integral we're going to take with respect to t. Now, one of the things that is cool to notice is what we have right here. This square root that we have is the magnitude of r prime of t. So notice it's that derivative of our curve that we're integrating over and then taking the magnitude of that. Now, one really interesting thing to notice as well is that if f of xy is just the function 1, then this integral is the arc length formula, which we had learned that back in chapter 12. So that was in, let's see, 12.5. So what happens then if you just integrate the function of 1 over this curve, what you really get then is the arc length of the curve that we're integrating over. So it's sort of analogous to then that idea of how we have done integrals where we have integrated over areas of regions. So that was like our double integrals. So that's like when we did the double integral over r of like some function and we would do it dA. We did integrating over volumes of solids. So that was like a triple integral over some solid q of f, and we did it dv. And remember, in both of those too, if f was 1, the top one, the double integral over r dA just gave area between curves, so area of that region. And when f was 1 in the second one, it did give the volume of that solid q. So then now we're integrating over arc length of a curve. So that we've got that integral over c of f, and we do it ds, is what we've got. The formula up top that we gave was for plane curves, two variables. We can also come up with just the analogous formula for three variables. So if we have three variables, if c is, let's say, r of t has x of t I plus y of t j plus, say, z of t k, where again t ranges from, say, a to b. Then if I integrate over c some f of, say, x, y, z ds, so integrating over the curve c, Then we're just going to have, again, the integral from a to b. Now I've got three things to plug in, so f of x of t, y of t, z of t, so that will turn f into a function of t. And then now my square root is going to have x prime of t squared plus y prime of t squared plus z prime of t squared. And we're going to take that whole thing dt. So we'll integrate with respect to t there. So really it just adds in that third component. And again, when we did have three-dimensional space curve parametric equations, this is still the magnitude of r prime of t. It just has a third component to it now, which that was our definition of arc length, was to integrate over the interval of the curve, integrate the magnitude of the derivative r prime. So what we can do is we can try some examples of this. So we'll do that in our next video, but we're just going to give some example functions and some example curves and try and find these line integrals.